Hello everyone, I'm Rekha Murthy from Electrical and Electronics Engineering Department from Sai Vidya Institute of Technology. Today I'm here to continue with the next session of the Module 2, where it is of the overcurrent protection and the distance protection. So, in this session, we are going to discuss about the protection of parallel feeders, protection of ring mains, earth fault and phase fault protection, and combined earth fault and phase fault protective scheme. Now let us go with the protection of parallel feeders. Here, this diagram, it shows that this is the overcurrent protection scheme for the parallel feeders. So where here at the sending end of the feeders at A and B, the non-directional relays are required. So here the symbol, what is this symbol bi-directional you can see? This is a indication of a non-directional relay. So at the other end, this is the feeder lines. This will be the source side, and here this is the feeder line. So the feeder line is at the position of the C and D. Okay, where here also we have located the one of the relay. So the direction is only in the one direction. This indicates it is a directional overcurrent relay. The arrow mark for this directional relays is placed at this C and D. Okay, that indicates that the relay will operate. That indicates that the relay will operate if the current flows in the direction which is shown by this arrow. Okay, suppose now if a fault occurs at F, that is this position, if the fault occurs at F, the directional relay at D will trip. This directional relay at D will trip, as because the direction of a current is reversed. Because this direction of a current is reversed. The relay which is there at the B will trip for a fault. It will the relay at B also trips for a fault at F. So thus we can say that the faulty feeder is isolated and the supply of a healthy feeder is maintained. Here what you can see, the fault has occurred here and the direction of the flow of a current is in this way. It is following up. So the relay D should trip, and as well as the relay B should trip. Due to this non-directional, what it will do, it will change the direction of the current in a reverse order. So this is how it is going to flow into it. Okay. Fine. So if suppose non-directional relays are used at the position of C and D, let us assume that this non-directional relay is used at the position of C and D, and both relays are placed at C and D, will trip for a fault at D. So, but when you place in that fashion, that is not the desired one, because the healthy feeder is also get tripped. So due to this reason, the relay at C and D should be always a directional overcurrent relay. So for a fault which is there at the feeders, the direction of a current at A and B, the direction of a current at A and B should not change. And hence, the relay which is used at A and B should be a non-directional, not at this condition. Make sure at the source side, we have to prefer the non-directional relay. At the load side, we need to prefer the directional relay. which will make a possibility to reverse the flow of a current whenever the fault is going to occur. So at the load side, it is going to take care. But make sure at the source side, there should be always a presence of a non-directional relays, which should not change the direction of flow of current. That is about this parallel feeders. Okay, fine. Now coming to the next topic, that is how we are going to protect in the different fashion. You cannot always assist that the feeder lines will be always in this fashion. It can be in a different way. It can be in a different type. The mesh will be there, but in a different manner. It can be different shapes. Okay, how you can connect it, right? Fine. So let us see that in what manner you can see. It can be in the type of a ring manner or some other different types. Okay. So let us see the protection of a ring mains. Ring mains. Now let us concentrate on to that the diagram, which shows an overcurrent scheme for the protection of a ring feeder. Okay, this is a protection of a ring feeder. One more diagram we are going to take up to explain this topic. That is, that diagram will be an another way of drawing this the same scheme. This same scheme we can draw in another fashion. That is like this. Okay, fine. Now, compared with the radial feeders, the protection of a ring feeder is found to be costly and it is a little bit complicated. Here, each feeder requires the two relays. Each feeder will require two relays. Okay, so a non-directional relay is required. A non-directional relay is required at one end and a directional relay at the other end. Make sure that each feeder requires a two relay. One is a non-directional relay at one end and another one is a directional relay at the other end. Okay. Now, what about the operating time? The operating time for these relays should be considered by having a grading first in one direction and the another and then in the other direction. Okay, which you can see here in this diagram. Okay, the grading you can see here how much the grading time I have provided 0.1 second, 1.1 second, 0.6, 1.6. This is how we have to segregate it. Suppose now let us consider this diagram. If the fault occurs at F1 position, which relay is going to trip? Okay, find out where is F1. Which relay is going to trip? Nearest to this F1, C dash is there and D dash is there. Obviously, C dash and D dash will trip to isolate that faulty feeder. The relay at C will not trip because as the fault current is not flowing in its tripping direction, though its operating time is same as that of the C dash, that is why this C should not react. Okay, fine. Again, I will repeat, the relay at C will not trip because the fault current is not flowing in its tripping direction, though its operating time is same as that of the C dash. Similarly, the relays at B and D, the relays at B and D, that is also should not trip because as the fault current are not in the tripping direction. They are not in the tripping direction. Though their operating time is, how much it is? 0.1 second. It is quite less. It is quite less than the operating time of B dash and D dash. Okay, that is what about the fault F1. And here the diagram which you can see, this is another way of drawing the same scheme. Okay, so in this figure, what you can see in this figure, the here you can see that in this figure, the loads, even the loads is not, loads though present, they are not shown here on this buses. A, B, C, D. Okay, so this will be the value A, B, C, D. So A, B, and D. To make the figure simple, we have taken this part of the circuit. Okay, so this is in between of the in feed line and coming to up to the CC dash position. So to make it very simple, we have drawn in the parallel way as what we studied in the previous slide. Now, if suppose just now I have discussed when the fault F1 occurs, what are the two relays should trip. Now, for example, if the fault F2 occurs, okay, if the fault F2 is going to occur, then the relay at A dash, then the relay at A dash, the relay at, when the fault F2 occurs, the relay at A dash and D will trip. It is understood, right? So that is how you have to analyze with, that is how you need to analyze with this. Okay. Now let me show the another diagram. Yes. So here this shows a scheme which will involve the more greater number of feeders. Okay, if you have more number of feeders, this is how the diagram will looks like. Okay, so here you can just see that how well the time grading has been increased further and further. Okay, if you assume that so many seconds of a time will it take to trip this relay, then 1.6 for the A, which is higher, almost it is a highest value of a time will be consumed at the source end itself compared to that of the load side. That you have to make it assure. Fine. And also the remaining relays like B, C, and D, whatever is there, the value of the time grading should be less compared to that of the which is there at assigned at the source side. Similarly, here what we have done, if you increase the more number of feeder lines, definitely you will find that we are going to increase the value of this 1.6 is getting increased to 2.8. Okay, then further you can just distribute it with a different time gradings for the next release. Done? Okay. So this is what the you can analyze with the different what you say that different faults at the different points. But one, make a note of it that a non-directional relay should be always presented source side and directional relay is present at load side. Okay, and one more thing in between of this, if you are placing a many number of many number of the sectionalization when you're going to do, we need to place the both the directional and non-directional together. So each sectionalized part is getting separated by the one directional relay and one non-directional should be there. Okay, in order to follow if suppose the fault current is going to occur, the relay when it is going to trip, it indicates that it has to reverse that current. There will be a reversal of a power, right? What we had discussed in the previous session. So that reversal, for the making that reversal of power, we require the directional relay. That itself indicates when the reverse of flow of current is going to flow, that indicates that particular relay has to trip. So that immediately from source end, the directional flow of a current will not get changed at the source side. It is going to change only at the load side. So the load side will identify whether that is a fault current or whether it is a normal current. Okay, as it is flowing in a reverse direction means that itself indicates there is a fault. Okay, so for that purpose we require the directional relay. Fine. This is, I hope you have cleared. Next concept is about the earth fault and phase fault protection. So in this case, the earth fault and phase fault protection, a fault which is going to involve the ground is called as a earth fault. Do you agree? So what are the examples are there? It can be like line to ground fault, double line to ground fault, right? Those are all the fault which involves a ground. The fault which do not involve a ground, that is called as phase faults. That is called as phase faults. So there are protective schemes which are going to use for this protection of an element of a power system against this earth fault is called to be as earth fault protection. Earth fault protection. Similarly, the scheme which is used for the protection against a phase fault is known as a phase fault protection. Okay, I hope you have cleared. Now, so here the earth fault relay and overcurrent relay. The relays which are used, for the protection of a section of a power system against earth fault, they are called earth fault relays. Okay. Similarly, the relays which is used for the protection of a section of a power system against the phase fault, those are all called as phase fault relays, or it is called as overcurrent relays. Okay. So the operating principle and all that construction features for both of these relays, earth fault as well as a phase fault, will be same. But the only difference is that depending on the current levels of their operation. Because the plug setting for the earth fault relay is going to vary between the 20% to 80% of the CT secondary ratings in the steps of 10%. In the steps of 10%. And earth fault relays is more sensitive compared to that of a relay which is used for the phase faults. And what the plug setting for the phase fault relay, that is going to vary between the 50 to 200% of the CT secondary ratings in steps of 25%. So the name, the phase fault relay or the phase relays, is not common. The common name for such a relay is the overcurrent relay. Okay, overcurrent relay. So if anybody should not confuse you this term about what is the overcurrent relay and phase fault relay. Both are the same. Okay, generally a relay which operates whenever the current exceeds its pickup value, that is called as an overcurrent relay. Right? Here, in the case of a phase fault protection and earth fault protection, the relays which are used for the protection of a system against the phase fault, they are called as a overcurrent relays. That you have to remember. So this is a new thing which you have learned in this session. And another way of defining an overcurrent relay. Okay. Now coming to earth fault protective schemes. So an earth fault relay, an earth fault relay may be energized by a residual current. So let us see here the figure. In this case, the IA, IB and IC, they are all currents in the secondaries of a CTs of a different phases. When you sum up these currents, that is IA plus IB plus IC, that is called as a residual current. So under a normal conditions, this residual current is zero. Whenever an earth fault is going to occur, then the residual current is non-zero. When the earth fault occurs, then the residual current is non-zero. So whenever it is going to exceed, okay, it's a pickup value. So whenever it exceeds the pickup value, then what will happen? Then the earth fault relay is going to operate. Okay, so in this scheme, what will happen? The relay operates only for the earth fault. So during a balanced load conditions, during the balance load conditions, the earth fault relay is going to carry no current. Hence, we can say theoretically that its current setting may be any value which is greater than 0. But practically, it is not true as what you are understood in theory. Usually, what happens? The minimum plug setting is made at 20 or 30%. It will be there. And whatever the manufacturer is going to provide you, a range of plug settings for the earth fault relay is from the 20 to 80% of the CT secondary ratings with respect in the steps of 10%. Okay. So the magnitude of this earth fault current is mainly depending upon to the fault impedance. So in case of an earth fault, the fault impedance is mainly depending upon to the system parameter and also on the type of the neutral earthing. So the neutral may be solidly grounded. So grounded either through the resistance or it can be through the reactance. The fault impedance for this earth fault will be much higher than that of the phase faults. So hence the earth fault current will be very low compared to that of the phase fault currents. Okay. And here this earth fault relay is found to be set which is independent of that of the load current. And even its setting is below the normal load current. So whenever you find an earth fault relay is set to a lower value, then its ohmic impedance value will be very high, which results with the high CT burden. Okay. Now let us see. I would like to show a diagram where that is this diagram. That is this shows that an earth fault relay used for the protection of a transformer and as well as an alternator. Okay, and whenever an earth fault occurs, the zero sequence current is going to flow through the neutral and it is going to actuate the earth fault relay. Okay, so this is where this part of a circuit is indicating about the earth fault relay, which is mainly used for the protection of transformer as well as the alternator. So whenever the earth fault occurs, the zero sequence current through the current flows through this neutral. So then it will actuate the earth fault relay. Okay, one more diagram I would like to show where you can see that is a special type of a CT that is known as a core balance CT, that is which encircles the three-phase conductors, which is going to encircles this three-phase conductors. This is a ring type of a CT where you can utilize it for the protection of a earth fault. Okay, now let me consider one more topic that is related with the phase fault protective scheme. This is about the earth fault protective scheme. Similarly, you can go with the phase fault protective scheme. Then we can go with the combination of both of this scheme. So let me move on with the combination. There itself, I am going to explain you what is that phase fault protection scheme. This is what we are going to employ the phase fault protective scheme. So wherein this scheme is mainly used for the protection of the system against the phase faults. So there is no any separate scheme for the earth fault protection. Okay, and sorry, if there is no separate scheme for the earth fault protection, then the overcurrent relay which is used in this scheme will also going to sense the earth fault, but it will be very much less sensitive. Okay, so this is for the phase fault protective scheme. So the combination of this phase fault and the earth fault, you can consider this will be the diagram. So wherein we are going to consider the two overcurrent relays and one earth fault relay. So whenever an earth fault occurs, the burden on the CT, the burden on this CT is more active than that of an overcurrent relay. And the earth fault relay will be in series. So the CT burden is going to become very high and it may cause some saturation. So this is what happens whenever you combine both of the protective schemes. So finally, I would like to conclude that we had discussed about the protection of parallel feeders. So where we got an information about how, where and all we need to place the relays, directional relays and non-directional relay. And also we discussed about a particular point which we had considered in the ring means which relay has to be tripped and which should not be active. And we had also discussed about the earth fault protection and the phase fault protection and what is the difference between the two, and when you employ both of them combined, earth fault and a phase fault, so what are the what effect it is going to cause in the CT burden value. Burden value is nothing but it is indicating about its the MVA capacity. Okay, burden is nothing but usually it will be expressed in MVA. That is nothing but a loading capacity, how much the CT can be able to load. Okay, so that is about, that completes about the all these different schemes. Okay. Thank you for watching this video.